absolute value function. If you look, for example, at f of x, which is defined down here, it's going to be made up of two functions. It will be made up of a negative x and an x. So it has two different expressions. What do we call those functions, if you remember? Piecewise, that's right. Okay, so we have to determine the domain on each side, and in this specific one, absolute value function, we have less than or equal to 0 and then greater than 0. And obviously you can switch the equal sign from one to the other because they will overlap with 0, 0. Okay? So to the left of x is 0, we have a negative 1 slope, so it's a linear function, just like any others. If I graph it, it just keeps going. And then on the other side, it has a slope of 1. It's also a linear function. And if I were to graph it, I would just get a v function, sort of like this. So f of x. Okay, so some features, it goes through 0, 0, very similar to the parabola. Okay, so it goes through 0, 0. And we will denote this with a different expression. So instead of writing the piecewise expression with those brackets, we'll just denote it as x within two lines. Okay, so two straight lines. So that's the modulus function or the absolute value. Okay. And notation, you're going to use f of x is equal to absolute value of x. And you don't have to state anything about the domain like you have to in the piecewise expression. Okay? So the domain here is made up of all real values of x, and the range, what do I have to add to the range? Yep, greater than or equal to 0. So if you think of a few points, you can always note 0, 0, 1, 1, and negative 1, 1, just like with the quadratic function, okay? Just remind yourself. But in general, if you remember that it's a v function, then everything's good. Okay, so let's see what it would look like transformed. So I could have, let's say, a g of x transformed. So I could have, let's say, a g of x. And we'll only graph one, but we'll give the expression for a few of them. Okay? So let's say I have a 2 times x plus 3. So my original function, absolute value of x, is right here. So if I determine my p of x, that's right in there. So that now allows me to read the transformations, right? There's one here, and there's one right here. And we said order of operations, we always start with what? When we look, yep, multiplication and division. And what does this 2 tell me? Okay, so it's a vertical transformation, first of all, and it's a stretch. Why is it a stretch and not a compression? Yep, greater than 1, that's right. Okay, so if we were to say the factor by a factor of 2. The 3 tells me what? Now I'm adding a value, and I'm adding to x or to y? Which one of the two? To the y, that's right. So again, it would be a vertical. And what do we call this transformation? Adding a translation. And if we quantify this, how much am I translating in which direction? 3 up. Okay, so I'm only going to mark down the points of the parent function, not drawing it out fully, but I have a 0, 0, 1, 1, and the negative 1, 1. And first, that's getting vertically stretched. So the 0, 0 won't go anywhere, but the other 2 points, what happens to them if they stretch vertically? Yep, so the y value times 2. So they would go to somewhere here. But then I'm translating them upwards. So what's going to happen here? What do I do with the pink points? 3 up, yep. So I'm going to go with here for the first 2. And also the vertex now, so-called vertex, moves up to 3. So this would be my absolute value function, transformed. Okay, so we'll do a few more, but we won't draw them. You can draw them if you'd like, but we just want to interpret what's happening to the actual parent function. So let's look at an h of x, and let's say it's 1/2 or 1/3 x plus, let's say 1, and all of that is an absolute value. What would I need to do first here? Most of these transformations, all of them are horizontally occurring, right? So only the x gets affected. But there's something here that I need to modify before I can interpret it properly. We said the stretches and compressions stay as they are, but the translations, unless I factor, they won't show properly, right? Matilda, do you want to add something? Okay, so factor what here? 1/3. Okay, so I stay within this absolute value, but I'm factoring out a third, and that leaves me with an x inside the bracket. What happens to that 1, though, once I factor out? Yep, that's right, so plus 3. So now if I look at this, I can isolate the horizontal, and we'll talk about what that is in a second, and the other horizontal transformation. Okay, if I were to initially interpret it through 1, I would have been misled to think that it's going to the left or right. We'll see what happens there by 1, but it's actually going left or right by 3, right? Sorry?
So why is it 1 over 3 horizontal?
Because it's within the absolute value. So the one that changes is the x value, not the y. So when you see a number outside the absolute value, then it's the y converting to a larger or smaller. Okay, and we'll do one where we have both, just so you can see the difference. Okay, so we have horizontal there. What happens? Is it vertical? Is it compression or is it a stretch? It's a stretch, that's right, because we're going horizontally, and by a factor of 3. And the horizontal translation, is it to the left or to the right? To the left. By 3. Okay, and let's do one more. We'll throw in a reflection too, where we combine a vertical and a horizontal, because there was a question about that. So we have, let's say, k of x, and we'll say 5, then absolute value, and then 2x plus 1, and let's say minus 3. And let's put a negative in front of the negative 2x, okay, and see what happens with that. And no, you won't, on a test, you wouldn't get so many transformations, just so we can distinguish between them, okay? So the 5, what will that tell me? A vertical stretch. Okay, it's outside the absolute value. For this one, though, I need to transform it. I have a negative 2x, so I'm going to factor out the negative 2, and we have an x minus a half. Okay, so it looks quite a bit different once we factor it out. So we have a negative 2, and that now behaves as a reflection into the y-axis. And then we have also the 2, which is the stretch. Okay, so, or not stretch, but horizontal compression by a half. And the last one, these two refer to our translations. I'll write them in one step. So translations, horizontal and vertical, and we're going to the right and down. And quantifying it is a bit easier, so a half and 3, to the right and 6. Yeah. Sorry? Yeah, we already talked about the vertical stretch. Yeah, you can write it in whichever step you want. Okay, so for these, all you have to do is be able to read off the transformations. Remember the general graph, right, the V shape? But there's no algebra involved like in the other functions, in the quadratic, the radical, etc. Okay, so now let's move to the cubic function. First of all, some votes. What do you think it refers to? We've talked about the quadratic over and over again. What might the cubic refer to? So if your quadratic is x squared, what do you think the cubic refers to? X cubed, that's right. So exponent turns to a 3. Okay, so you can graph this using some points, right? A table of values. So let's say here, x and y. You don't have to do this every time. Once you see it once, you'll probably remember. So x and f of x, or the y, 0, 0. If I plug in x as 0, what do I get for y? A 0. If I say negative 1, what happens with the y value? Also negative 1, but I'll write it in full. So negative 1 cubed, right? And that gives me a negative 1. And we probably won't be able to grab this one, but I'll still write it down. So if I go negative 2 cubed gives me what? Negative 8, that's right. Okay. And then with 1 cubed gives me a 1, and 2 cubed gives me an 8. Like I said, the outer points there we probably won't be able to graph, but so you have a 0, 0, a 1, 1, a negative 1, negative 1, and it goes further up. But the point here is it behaves just like with the quadratic, where you have that nonlinear dependence. So you go pretty quick. So it's a steep slope into the first point, and then a lower slope, and then it goes to a 0 and keeps going upwards. Okay, so these 3 points are the main ones you should know, especially for transformations. And this one in general is a bit tough to graph when you talk about vertical stretches. But as long as you show these 3 points, you should be okay. So the 1, 1, if you have a vertical stretch, is the only one that you can draw appropriately. So features, again, it goes through 0, 0. As a reminder, some other points that you'll use are these ones, -1, -1, 1, and 1. The domain and range, I'll let you tell me what I have to write down for the domain. Is it different from the quadratic function? What do you notice for the domain? Does it have any restrictions along the x? Nope. So all real values. What about the range? Yeah, unlike the quadratic, this one is all real numbers. Okay, so the y continues infinitely up and down. Quadratic functions, and you don't have to write all of these down, but you could have things like 3x cubed plus x squared. I'll put a dot and then list them. You could have negative x cubed minus 1, etc., etc. Okay, but we'll only work with the ones that are already in factored form. So if I look for a transformed function, let's say, you will usually see them like this. So x minus 1, let's say all cubed minus 2. Because you could unfold this and show it in polynomial form, right, with all the x values and exponents of 2, of 1, etc. But you won't be asked to do this. So as long as you recognize it in its factored form, that's all you have to do for this unit. Okay? Next year, you'll learn how to break these down and turn them into factored form. But the algebra is not part of what we're doing right now. But once again, you should be able to recognize the cubic and now read the transformations, which is just like any other function, right? So if I compare this to the parent function, which was just x cubed, I notice that this 2 gives me a vertical transformation, stretch or compression. This will give me a horizontal stretch translation, and this will give me a vertical translation. So nothing changes in terms of how you view these functions, as long as they're given to you in this factored form. Okay, so we have 2 gives me a vertical stretch, yep, by 2. What about the -1 there? Translation, am I going left or right?
Right.
To the right. And then the -2, a vertical translation. And like I said, these are a bit tough to draw, but we'll do the 0, 0, 1, 1, and -1, -1. And then operate on the vertical stretch compression, and so on and so forth. So you guys give it a shot, and then we'll do it together. So vertical stretch, the 0, 0 stays exactly where it originally gets placed, and then we get a vertical stretch by 2. These 2 points move out to a y of 2. And then for the horizontal translation, I'm going to the right, and that's 2 units. So 1, 2, 1, 2, and 1, 2. Oh, is it 1? Yeah. And the last one, vertical translation, we're going down to 2. So that's 1, 2, 1, 2, and 1, 2. So it's a fairly steep function. Yeah. And as usual, those 3 points, make sure that you highlight them, because that's what one would be tracing to figure out your transformation. Okay? We can't really determine where the other points lie accurately, but this is the one. These are the 3 points that we can track. Okay? Once again, make sure you cover your grids. Should we look at one more, just as an example without graphing? Maybe? Yeah? Okay. So h of x is, let's say, -1/2, 2x, let's say plus 4, all cubed, and that's it. So what would be the first thing to do here? Factor out the 2, okay? And I could technically take it outside of that bracket, but I'm going to keep everything with the cube for now. Just like with the quadratics, there are 2 ways to interpret this. If you take the 2 out, you could move it into the vertical transformation, look at it that way. But if I factor out the 2, I get 2x plus 2, and I still have here my square brackets. So I haven't quite moved it, factored it all the way out, which I could. So if I leave it as it is, we'll simplify it one more way here. But as it is now, what does the negative tell me? Reflection about what? That's right, about the x-axis. What about the 1/2? Vertical compression by a half. And the 2 inside, it's a horizontal compression. Okay, and also by a half. And the last one, easy peasy, the 2 is what? Yep. To the left by 2.
could you just, instead of factoring out that you would have in brackets, could you just multiply it by the negative 1/2 and then factor?
Yeah, so that's what we said we're talking about that right now, right? So you can look at this in two different ways. I think you asked this last time in class too, right? So there are two ways to solve most of these problems, and either one is acceptable. Okay? But in terms of graphing, sometimes it's good to break it down into two. So we're doing this, but you don't have to do both methods every time. Okay? So in this case, if you do take out the 2 cubed, don't forget about the cube. You get a negative 1/2 times 2 cubed, which is an 8, and then x plus 2 still stays behind. Right? So now I can look at this, all of this term here. That's a negative 4 times x plus 2 all cubed. So you can read it like that too, whichever method you like. It's up to you. But like I said, most of these on a test or in the mid-year, you wouldn't have more than 3 transformations, so you wouldn't have to worry about all of this algebra in general. You just have to be able to remember the factoring, that's one of the main steps, and then interpreting each transformation. Okay, this one might be the toughest one because you haven't seen, I don't think, exponentials before. So I'll give you a few minutes, not to Google it, but to think about what it might mean. So if you think of a cubic function, you know it depends on the cube of the x. What do you think it might mean if you're looking at an exponential function? How might the y depend on x? Just looking at the titles. Because, well, yeah. But in terms of an expression, so you know for a cubic, you have x cubed. What might it be for an exponential? What might the expression be, in your opinion? Where would the x go? So you can talk to your partner 2 minutes or so. If you don't have a partner, find a partner. It's about to get a bit intense, so just take a 2-minute break and discuss this. Oh, sure. Leave the door open so you can. What? Yeah, the what? Exponent. Yeah. Now that leaves the question. So if you have the exponent, what will this be here? That's right, a constant. Yep. And it can be any number. Yes. Good work. Now go try convincing others.
I don't think you can convince him.
Oh, yes, you can. You can do anything. So somebody took a guess up here. They said something to the power of x, so x is the exponent. Do we agree?
Just agree.
Well, she has an argument.
It's like a number and then it's n in power to x.
Sure, you can think of it as n, but we usually think of it as x for the bit.
X and then plus something.
You could have plus something, that's right. Okay, do you need another minute, or is everybody convinced that the name exponential refers to the exponential dependence? So that goes into the exponent. Okay, so as a general, f of x is any number, so we'll usually call this b, okay, where b is a constant. That's not 0. So as any decent human would do, we'll do a table of values, x and f of x, and we'll say what happens when x is 0, what happens when x is negative 1, negative 2, 1, and 2. Just to get a rough idea of what that function might look like. So we said that's a constant, the b. So for now, I'm going to write it as, let's say, 2 to the x. So we'll just consider a value for b. So b is, let's say, 2. Okay? So then I get my y as 2 to the power of negative 2. What do negative exponents mean? Not a root, that's a fraction. You're thinking of a fraction, right? But if it's a negative value, then it turns this in front to a half. Okay? So it's 1/2 all squared. So I get 1 over 4. Oh, is that what you meant? Sorry. No. Okay. Okay, and then we have a 2 to the negative 1, which is 1 over 2. And then 2 to the 0, what is that? That's a 1. Then 2 to the 1 is 2, and 2 squared gives us back the 4. Okay, so let's try a bit of a graph here. So for 0, I have a value of 1. For 1, I have a value of 2. For 2, we go to 4. And then the other ones are a bit more difficult to graph. So negative 1 is a half, and negative 2 is 1 over 4. So we could label this axis 1/2 here, just so we know what we're talking about. So we have 5 points. We don't usually need to describe more than 5 for an exponential. Even 3 sometimes is enough. But what you want to highlight here is this point. Okay, and I'll give you maybe a minute to think about that and tell me why that might be important. Think in relation to this number here. So we arbitrarily chose a b of 2 because that can be any constant. You'll see this function in different ways. But Is there a relation between that b and the y-intercept there? Can somebody make an observation?
It's always going to be one there.
Always, yep, almost always, but yes, why? What's the reason behind that?
Because whatever you choose as your constant is going to be that number to the 0.
Yep.
It's always going to be 1.
That's right. So we have this power of 0, okay? So that means this will always give me the y-intercept. Now, it's not always going to be 1, but for now, we'll think of it as 1, okay? So it always gives you the y-intercept. You know, another observation to make here is we can't really draw many points on this side of the axis, right? But what can you note about the y value? So because it's this exponent to the negative, let's say, what is it, to the x? So 2 to the x. No matter how small you make this x, what will happen to this expression? Does it ever go through 0? Can you find an x? No? Okay, so this tells me that there's something happening at y is equal to 0 here, right? What do we call that? We sort of did this. Asymptote, that's right. Okay, so right at y is equal to 0, I have an asymptote. Oops. So I will highlight this. You don't have to highlight it every time, but you do have to label it. So the label of y is equal to 0 does need to go with all of your graphs. Okay? So when I graph this, I will connect these points to show the exponential increase. But on the left side, I have to be careful to just show that it goes infinitely close, but it doesn't reach the asymptote. Okay? But you do have to cover the entire grid. But once again, this is highlighted, so the asymptote should always be labeled, just because the graph does look a little bit sensitive to those distances. It depends on how neat you are when you graph. Okay, so this would be my f of x. So as a note here, you always travel, this is the positive direction going to the right for x. So what do you notice for y as you travel to the right? Does the y increase or decrease? Y increases. Okay, so this is exponential growth. Now you can also have exponential decay. And I'll give you 2 minutes to maybe write down an expression that would turn this graph into an exponential decay. So remember, here at the top we had f of x is 2 to the x. That's what we graphed. What's one way to get this to be a decay? So you can start with the graph if you want. So all the points that you have there just turn into a decay. So how could I do that maybe? There are 2 ways here. Let's say we keep the intercept. Okay, so we don't do anything special about the intercept. And the other point here was 1, 2. This is a half, and this is a quarter. What might the expression of that be? Do you want to go and write it at the board? Whiteboard, not the projector. Because the negative can go in many different places.
I will. No.
It's okay. The point is to experiment. Be adventurous. You have to write it down. You have to write it down. Do we agree?
Yes.
Yeah, because that would reflect it in the y-axis.
Yeah, but what would reflect it into the y-axis? That's a good idea. A good way to think of it.
Inside the bracket.
Well, what are we switching? What are we switching? We're switching the x's. So if you do think of it as a reflection, you would have the exponent be affected, right? The negative x. So it would be 2 to the negative x, right? If you were to think of it that way.
So she's pretty close.
Sure. But no, it's good to experiment, but yes. You can think of it that way. No, it's good. Just think back of your reflections, right? So if you're reflecting to the y-axis, you're switching the x-coordinates from positive to negative, from negative to positive, right? So that's one good way to think of it. But there is another way, too. So if I have a decay, remember before it was 2 to the x, right? But, and that gives me growth. How would I get a decay? What needs to happen going in time? It needs to decrease. How do I decrease? Using fractions, right? So if I use fractions here, it looks like the segment would be 1/2 to the power of x. Okay? So instead of a b of 2, I use a b of 1/2. It doesn't have to be a half. It's just we're trying to get the decay corresponding to this growth. Okay? But it could be any fraction. But the point is, if you have a fraction there to a positive exponent, it will be a decay. And you can go through points, or you can look at the algebra here, right? I wrote down or, but it's in fact an equal, right, relation between these two. Because if I write my rules of exponents, the negative x, all this negative x does is I have 1/2 and then all to the power of x. And they're identical. There's just 2 different ways to think about the expression. So we said this here thinks of it as a reflection, and this one just highlights the decay aspect of it. They're both correct, and they're identical, right? And then as a graph, disconnect your points. The asymptote stays identical, and the intercept stays identical, because we haven't changed anything about the nature of the function other than that rate, right, inside. So I still have to denote here. You don't have to highlight it every time, but I will label the asymptote. What do I label the asymptote as? What was it? Y is equal to 0. Okay, so that full line, and f of x is already labeled. Okay, so one more question I have for you is, how would I take this function and move it up or down? Two of the points are easy to grab and drop down, but what about the other two? Sorry?
Just change the b.
Well, let's say, that would be one way, but remember, if I want to go left, right, what were the operations for transformations? It would be addition or subtraction. That's right, right? So first I'm just going to grab those points. So we have a 2, let's say, would go to a 1. The 1 goes to a 0. Two of the points are easy to grab and drop down, but what about the other two? Sorry?
Just change the b.
Well, let's say, that would be one way, but remember, if I want to go left, right, what were the operations for transformations? It would be addition or subtraction. That's right, right? So first I'm just going to grab those points. So we have a 2, let's say, would go to a 1. The 1 goes to a 0. The 1/2, I'm moving everything down by 1. And the last one, also by 1, which is a quarter. Okay, and I'm not going to draw every single point, but what do I notice here? It's the asymptote that changes. Okay, so we have 4 points. We've moved 1 down. Henry, are you looking for something? You can go to the washroom if you need to. Okay, so 1 down, and I can go here my asymptote, which went now to a value of what? Y is equal to -1. That's right. So if I write down the full expression, I'm still working with the decay function, so that was 1/2 to the power of x. And what did we do to all the y values? We moved them down, that's right, so it would be -1. You guys can fill it in, but it goes -1 after the 1/2 to the power of x. Okay, so that's -1. So the transformation from the base function, in this case 1/2 to the x, is -1. So that's why, unlike the other functions that we talked about, even cubic, quadratic, all of those have one base function or one parent function. For these, you don't have one specific function. So it will all depend on b. So you look at b first, that's your base function, and then from there on you can assess all the other transformations. But you could have, for example, base function 3 to the x, base function 7 to the x, or 1/8 to the power of x. Okay? So there are several parent functions. It's not just one that you can talk about. Okay, so we're good with all of these? We'll talk a bit more about this next time, reflections. But for now, let's look at one full set of transformations. Okay, so let's say here h of x is, I'm going to take 3 to the x. Actually, no, let's say 2 to the x. 2 to the x. But what I'm going to do is give all the transformations possible in here. So let's say 2x minus 4 minus 7. And we'll put a negative on the -2. So first here, the base function would be, let's say f of x is just 2 to the x, because I identify that 2 as being the b. But I won't talk about the b itself too much, because you also have those letters in your transformations. Okay? But now, the first thing I need to do to read off the transformations is factor out the 2 in the exponent. Okay, so what do we notice here? What does the negative tell me? What transformation? Reflect into what? It's the y that changes, so yes, into the x-axis. And then here I have the x changing, and that will be a horizontal. With the 2, is it a stretch or a compression? Compression. Okay, by a half. And then I also have a horizontal translation to the right. And the last one is a vertical translation. And is it up or down? It's down by 7. I know, I guess you won't be able to graph this on this grid because of -7. But as long as you get the list of transformations, it's all good. Okay, so so for all of these functions, we'll talk about exponentials a bit more and interpret and see how they're applied. This is an actual function that's used in the real world as opposed to the absolute value function. Cubics, quadratics, all of those are useful, including exponential. We'll talk about this a bit more later, but for now, just be able to recognize the transformations, okay, and the usual factoring out your transformation so you can read off what happens properly, and also read off the intercepts here. So if I go to the y-intercept and the asymptote, I should be able to quickly assess what they are. So the asymptote is immediate from just the expression, right? Because I know that 2 to the 0, so you get a y as negative 2 to the power of negative 4 and minus 7, because my x value is 0 for the intercept. So that gives me a negative 1 over 16 minus 7, and then you can common denominate that, but that would be the y-intercept. And then the asymptote is y is equal to negative 7. Okay, so I think we're almost done, but all I want you to do now is practice maybe with the ones that I gave you earlier. So try to finish up, and I can do them in parallel, but these shouldn't be much of a surprise. They were on your last set of notes, as someone noticed. Okay, so I'm not saying go ahead and copy from your notes, but you should be able to do these because you've done them before. Okay, and if you have questions about exponentials, you can come up and ask now.